By now we've talked about the properties of acids and bases, and even done a lab or two, but we still have the pH calculations to accomplish. As you go through these slides, I want you to follow along and practice these practice problems. These are the type of problems that you'll find on the homework and on the test. Remember that pH is the expression of the concentration of the ions that determine whether something is an acid or a base. pH is a log expression of the acid concentration, the molarity of the hydronium ion, where pOH is the log expression of the base concentration, the hydroxide ion concentration. pH values and pOH values can add together for a solution to equal 14. Therefore, if you have one, you can calculate the other. On the pH scale, 7 is neutral. Those numbers lower than 7 belong to the acids, where the concentration of hydronium ions exceeds the concentration of hydroxide ions. However, substances with a pH of greater than 7 would be bases, and these substances have a concentration of hydroxide ions greater than the concentration of hydronium ions. In this problem, it states that the pH of the hydrochloric acid solution is 2.54. The question is, what is the pOH? Since the sum of pH and pOH is 14, we can rearrange this to solve for the pOH, which in this case is 2.54. So that our answer is 11.46. In dealing with the concentrations of acids and bases, we find ourselves using scientific notation more than usual. Therefore, let's review quickly how scientific notation can be manipulated and/or calculated. The first one says, write this number as a decimal, 1.0 times 10 to the negative 3. In order to write that as a decimal, we're going to need to move the decimal 3 places to the left of where it is now. As a decimal form, this number would be 0.001. If we're considering significant digits, the final 0 would remain. The next says, write this number in scientific notation. Proper scientific notation places one digit to the left of the decimal and the rest to the right. In order to write proper scientific notation, the exponent is a function of how many decimal places we will move the decimal. In this case, it would be 2, 3, 4, 5. So the answer is 4.5 times 10 to the negative 5. These two numbers have the same value, they're just expressed in different ways. The next one says, which number is greater? Since they both begin with 1, the difference will be in the exponent. Numbers with a smaller negative exponent are actually closer to 0, giving them a greater value than numbers with a larger negative exponent value, because that would be farther away from the main position next to 0. So in this case, 1 times 10 to the negative 4 is greater than 1 times 10 to the negative 8. When we multiply these scientific notation expressions, the digits multiply to each other. 1 times 1 is 1. The exponents add. So that negative 3 plus negative 4 would equal negative 7. Division is the opposite. You subtract the exponents when you have a division problem. Again, we look to the whole numbers, 1 and 1. 1 divided by 1 is 1. The exponents, negative 11 minus a negative 5, and minus negative 5 makes that a positive 5, results in a negative 6 for the exponent. Our next calculations involve the ion concentrations. The Kw is the ionization constant for water. It's the product of the hydronium ion concentration and hydroxide ion concentration. In pure water, each of these has the same value because they would be in balance, 1 times 10 to the negative 7 moles per liter, or molarity. Multiplying those two values to each other results in a value of 1 times 10 to the negative 14. Having this equation and this answer allows us to solve for one or the other of these concentrations with a little bit of simple algebra. This question asks, the concentration of a hydrochloric acid solution is 1.0 times 10 to the negative 5 molar. What are the hydronium ion concentrations and hydroxide ion concentrations? Because this problem is about an acid, this concentration that's stated is the hydronium ion concentration, since the hydronium ion is the acid ion. So one answer is given. We just have to analyze which answer they have given us. In order to calculate the hydroxide ion concentration, we will use the formula Kw is equal to the product of both the acid and base ions. And we will rearrange this equation to solve for our unknown. In this case, the unknown are the hydroxide ion concentrations. We'll take the ionization constant for water, which is 1 times 10 to the negative 14, and divide that by our hydroxide ion concentration, which was given in the problem, which is 1 times 10 to the negative 5. Okay. Using our MAD scientific notation math skills, we can see that 1 divided by 1 is a 1. For the exponents, we have negative 14 minus a negative 5, which makes our final answer negative 9. This says, calculate the pH of a 2.77 times 10 to the negative 5 molar hydrochloric acid solution. Because this is an acid, this value given is the hydronium ion concentration. So we just need to answer the question with the information given. 2.77 times 10 to the negative 5 molar. Calculating pH is the negative log of the ion appropriate to the substance. Hydronium ion if we're talking about an acid, hydroxide ion if we're talking about a base. All we have to do is plug this number in and take the negative log, and we'll have our solution. The answer is 4.56. This wheel is a tool that can be used to convert back and forth between information like ion concentrations or pH. Depending on the complexity of the problem, starting at endpoints, this sometimes serves as an easy way to map out the path to work the problem. When we do the titration reaction, it's based on the molarity rule, which states that at the equilibrium point, the concentration and volume of the acid is equal to the concentration and volume of the base. In order to calculate this, we have to take into consideration the equivalence, or the number of the ions. For an example, H2SO4 is made up of 2 mole equivalents of ions. In this example problem, we're given some information about the acid and the base, and we're left to solve for one component of it. It says 25.2 milliliters of 0.0220 mole sodium hydroxide were used to neutralize 35.0 milliliters of hydrochloric acid of unknown concentration by titration. Calculate the concentration of the hydrochloric acid and calculate the pH of the hydrochloric acid. First, we want to identify the acid and the base in the problem. HCl is the acid, NaOH is the base. Looking at their formulas, we see that there's one hydrogen in HCl, therefore it has one acid equivalent, or acid ion equivalent. NaOH has one OH, so it has one base ion equivalent. If we take the molar ratio equation and rearrange to solve for Ma, we do this by dividing both sides by Va to get this formula here. Substituting in the given information from the problem, we see that we don't have to convert the volumes of the acid and base as long as they're the same unit. And the resulting unit for the answer is molarity, which is the concentration, which answers the question, what is the concentration of the hydrochloric acid? Using that information, we can use the pH equation of negative log of the concentration of hydronium ions to find the answer for the pH, in this case 1.8. Let's work one more of these. This says, what volume of 0.0125 molar calcium hydroxide is needed to neutralize 50 milliliters of 0.0336 molar sulfuric acid in a neutralization reaction? The acid is H2SO4 with the two hydrogens. That would be 2 ion equivalents. The base, CaOH2, calcium hydroxide, has 2 of the OH ions. That's 2 equivalents. Therefore, we take the base equation and we put in these values for the equivalents because that will affect the concentration ratios. What we don't have is the volume of the base, so that's what we're going to calculate for. Rearranging the equation to solve for the volume of the base, it looks like this. Notice that in this example, the equivalents wind up canceling each other out. Now let's substitute in the given information. Now that we've put in the given information, we can see that molarity is the unit that's going to cancel. The remaining unit is milliliters, which will be the appropriate unit for the volume of the base. Now let's do the math. To the correct number of significant digits, our final answer is 134 milliliters of calcium hydroxide.